Let us discuss about the physical properties of earth materials. Before starting the video, please subscribe the channel and check the playlists for concepts of geology, geophysics and instruments. Geophysical methods of exploration depends generally on the differences in certain physical properties of rocks. This is to help in discriminating different rock types and also in locating the mineral deposits. While rocks and geological formations possess a large number of physical properties, only some have found use in geophysical exploration. The various properties are electrical resistivity and polarization, seismic wave velocity and certain nuclear geophysical properties like absorption of neutrons. These properties are found to show variation with the amount and quality of water available in a rock. In addition to these, the density and magnetic properties of rocks are also utilized for purposes of geological differentiation. We will discuss each property one by one. Electrical resistivity of rocks. The electrical resistivity of a formation describes its ability to conduct electricity. In practice, the units of resistivity are defined in terms of the ability to conduct direct current. It has been observed that the electrical resistance, R, of a material is proportional to the length, L, of the travel of current path, and is inversely proportional to the area, A, of its cross-section. The constant of proportionality, ρ, is characteristic of the material and is known as resistivity. Thus R equals ρ into L by A. From the above it follows that ρ equals R into A by L, and is expressible in terms of ohm length units. Resistivity is commonly denoted for prospecting purposes in terms of ohm meters. Its inverse known as conductivity is denoted in mhos per meter or Siemens per meter. The resistivity of rock formations depends on such internal factors as the mineralogical and chemical content, grain size, porosity, texture, structure. Other factors of external origin such as moisture, salinity, temperature also influence the resistivity of the formation. The resistivity of geological formations in general is very high under dry conditions and is reduced only where conductive materials like clay, sulfide ores or carbon are present in substantial quantities. In general, a rock formation is never completely dry and therefore may be represented by a two-component system consisting of the mineral matrix of high resistivity and the porous spaces occupied by moisture of low resistivity. The resistivity of moisture itself depends on the type and the amount of dissolved salts present in it. Pure water is a rare occurrence in nature and water generally contains a small percentage of some salt or the other. The more common salts which affect the electrical resistivity of water are sodium chloride, potassium chloride, sodium bicarbonate, magnesium sulfate, and sodium sulfate. It may also be noted that the electrical resistivity of such solutions also is dependent on the temperature and decreases with an increase in temperature. In natural conditions, sodium chloride generally contributes to 70 to 95% of the total salts occurring in formation waters. Hence, formation waters can be considered as solutions of one common salt. The presence of moisture-containing salts in hard rocks is limited to very small amounts due to the inherent low primary porosity, usually not exceeding 1%. Even small changes in moisture content at these amounts could however cause very large changes in resistivity of such rocks. Different types of rocks such as basalt, granite and dolomite exhibit a change in resistivity of the order of 1,000 times, due to a change in moisture from 0 to less than 1%. In more porous rocks, however, the relationship between the moisture content and the resistivity is somewhat different. For porosities and ranging between 4 to 40%, the resistivity of the rock is found to be proportional to the resistivity of the moisture. The constant of proportionality, which is called as the formation factor, F, reflects the effect of cementation and structure of grains. It is well known that resistivity of formations depends, besides moisture, on the lithological content and more so on the grain size for arenaceous formations. Rocks with clay content generally possess lower resistivity. For sandy rocks, the resistivity depends on the grain size, increasing with the grain size. The highest resistivity values are observed for gravels and pebbles, and lowest resistivities are observed for clay formation. In the next video we will discuss about the induced polarization property in the rocks.